Hello and welcome to the Cosmic Shambles weekly Sunday question and answer session. We're here every week answering all the questions that come out of your heads during the week, those little science things that knock around you never quite get around to asking. That's what we're here for, basically scratching your science itch. And we've got lots of questions for today. Don't forget, you can still send them in. If you've just remembered a question you had this week, do send it along to Cosmic Shambles via Twitter or the email address, and we will do our best to answer as many questions as we have in the time that we've got available. And a little bit more admin before I introduce our two guests, which is that, as always, Patreon is one of the engines that keeps all this kind of thing running in these times. So if you are able to donate to Patreon or support Cosmic Shambles via Patreon, that is very much appreciated. It does mean things can keep running. And there's also a tip jar. If you're a one-off viewer, you're not sure whether you're going to come back, but you would like to donate, it's not obligatory, obviously. We want to share as widely as possible, but there is a tip jar, and the links for Patreon and the tip jar are somewhere below this screen. A few other little things. So there is a science book Shambles that has just started, and the first episode is out now. And the first guest is the very excellent Paul Nurse, who was president of the Royal Society and has just written a very good book on the cell. And so there's all kinds of, he's got very interesting things to say. So that's the first episode of Science Book Shambles. There is also an extended edition. If you're a Patreon subscriber, you get a little bit more of Robin and Paul. I won't say ranting, but being opinionated about things. So other things that are going on, the latest Genetics Shambles, so that was last Wednesday, that was live, and it was a COVID-19 expert panel. It's still up on the YouTube channel, and you might see little short clips from it appearing in the Cosmic Shambles Twitter feed. And that is because there's a lot of debate about things now, and science comes down very firmly on one side rather than the other of a lot of those debates, like wearing masks. So if you haven't heard that episode, it's well worth watching, just because they really get to what is the evidence behind some of the recommendations that are being made. It doesn't tell you about policy. It does tell you what we know now about what the science says and how that's changed over the past few months, or maybe it hasn't changed. So that COVID-19 experts panel, which was an episode of Genetics Shambles, is now available. Highly recommended. Do ask questions in the live chat or on Twitter. We're at Cosmic Shambles. And next week, we've got a lot to get through, but next week we've got particle physics. So particle physics and all that distant stuff is next week. This week we are much closer to home. And one more thing, on October the 5th, which is not that far away, I'm a bit scared by the idea it's already October nearly, there will be a big Cosmic Shambles announcement. Something bonkers is about to happen. That's usually what that means, and it definitely does in this case. So look out for a big announcement around them. And if you're on Patreon, you get to know a little bit earlier than everyone else. So without further ado, let's come to... Oh, Robin's not here this week. Sorry, you might have noticed that. Probably should have said that at the start. Robin is indisposed this week, so I'm here instead. And we have two brilliant guests. We have Dr. Helen Scales, who's a marine biologist. Long-lived interest in fish, not just because of her name, but otherwise. And she's also got a new book. She's written lots of very good books, and she's got a new book coming out early next year, which we'll talk about. And we also have Dr. Nira Chamberlain, who is the president of the Institute of Mathematics and its Applications. One of those really good, very long job titles. I always want to try and turn them into an acronym and see if they spell out something that's either funny or embarrassing. Anyway, so how are you both? What have you been up to recently? Let's start with Helen. How are you?
I'm very well, thank you. Yes, I'm very excited. I'm out of quarantine, which is fun. So I went out into the beautiful weather outside here in Cambridge. That's because I was very lucky and I spent the summer by the sea, which helped me personally get through this whole ridiculous year very much. So I've been communing with the ocean for a few months, and I'm back now on dry land, but I'm very well. And looking forward to, I guess the only way to kind of deal with the next few months is going to be just kind of getting cozy and being inside and just embracing this cozy time of year. So that's my plans coming up.
We'll need to turn into some, like Norwegians or Swedes or something like that. Those people where they've really got the long winter evenings sorted out. Yes. Okay, so what's your show and tell? What have you got for us?
So I have got a very beautiful, very delicate, lovely thing. So I'm going to have to show you this. Hopefully you can make out. Can you see that?
It's transparent.
It is very transparent. It's incredibly delicate. This is a Nautilus shell. So, sorry, no, it's not a nautilus, it's an Argonaut shell, but a paper nautilus is its other name. So it's an Argonaut.
I was a bit confused, but I was about to be very excited. I was like, is this some bit of nautilus I've not seen before?
I don't know if this is a full-grown one, because there are different species of Argonauts, and some of them are a bit bigger, and this is a tiny one. This is the shell made by the only group of octopuses that make shells. All of the others have lost their ability to make shells, but the Argonauts re-evolved this extraordinary ability to make these incredibly delicate shells, and they make them in a totally different ways to all the other mollusks. So snails make shells by secreting calcium carbonate from their mantle, which is the sort of soft bit of tissue across their body. Argonauts make them from the end of two arms. They have basically kind of silvery webs on the end of two arms, and they make these beautiful shells. And it's the females that do it. And they use.
So where does the shell go on the octopus? If you make it at the end of their arms, what do they do with it?
Yeah, it's not attached, so they just live inside it and they hold onto it with their suckers. It's completely separate from the animal. So you could take an Argonaut out of its shell and it would be fine, and it could just go back in again if it wanted to. So they're not fixed like a snail. So you pull a snail out of its shell and that's it for the snail. But an Argonaut can come all the way out. And yeah, they are incredibly delicate, beautiful things. A friend of mine gave me this, actually. It came from Mexico. She found it on a beach and didn't know what it was, and so she brought it very carefully to me. And the other name, paper nautilus, is quite obvious because it's so delicate. And they're very cool. And for a long time, people didn't know what they were. There was a sort of question about were they actually some other animal that was a parasite on these creatures that made the shell, and that they went along and stole the shell from them. And one reason I love them is that the scientist who really figured out the science of Argonauts was a woman called Jeanville Power, a French lady in the 19th century. And she was like a kind of she was obviously very passionate about all sorts of things in nature, but she loved the oceans. She lived in Sicily, and she did all these amazing studies on Argonauts and worked out that, yeah, they do make their own shells, and they can fix them up if they get broken. They can't make a whole new one, but they can fix them. And they are these amazing shell makers. They're really cool. I should say I'm also appropriately dressed. I have one of my
And you've got a picture in the background as well, like a little Dumbo squid in the background.
That's an octopus, yes, if you see that there. Yes. So yes.
Very appropriately. We like people who come costumed. That's brilliant. Great. Thank you very much. Nira, how are you? And it's also awesome. How are you, and what is your background? Tell us about that.
I'm fine, thank you very much indeed. I'm doing good, and the background is of New York, because in this time we're not going to get a chance to travel, so I might as well see pictures of my favourite places around the world. Away we go.
Brilliant. And just before we get to your show and tell us about the Institute for Mathematics and its applications, because it sounds like that sounds like a very useful thing to me.
Yes, okay. So the Institute of Mathematics and its application is a professional and learned society for professional mathematicians, and our vision is to enhance a mathematical culture within the UK. It's been around since 1964. The first president, James Lighthill, who was involved in designing Concorde, and we had quite a number of prominent mathematicians who've been president since then. So yes, and we're one of the largest major mathematical societies in the UK.
Fabulous. All right. So what's the show and tell you've got for us?
Okay. So most people know about Schrödinger's cat. Is it alive or dead? So here we go. Schrödinger's ball. Here you go. So here we go. Is this ball orange or is it blue? Is it orange or is it blue?
I can see the audience votes arguing.
Is it orange or is it blue? Is it orange or is it blue?
Okay, we've probably caused enough arguments now. What's the answer? What is that thing? Because it's both, right?
It is both. It is both. It's both orange. It's both orange and it's blue.
Are you going to tell us what it was doing? Or is that some kind of magical secret we're not allowed to know?
The nice thing about this ball is that when you actually throw it in the air, there's a 50-50 probability that you actually will change colour due to its mechanics. So you throw it in the air, and what the inside will go onto the outside, and the outside will go on the inside. So henceforth, there's a 50-50 chance that it will change colour. So I just nicknamed this the Schrödinger's ball as opposed to the Schrödinger's cat.
That's great. So it's like flipping a coin. So we could use it at the start of a, well, we don't do it for badminton, but trying to think, football where they toss a coin at the start. You could instead throw up the mathematical Schrodinger's ball and see what state it comes down in.
Absolutely.
And is there some like interesting maths in that? Like, is that just a mathematician's toy for playing with probability, or is it doing?
I mean,
okay,
else? So now that yes, I mean there are some, let's say, interesting mathematics. I mean, it mostly relates to, let's say, to the mechanics. How can you move something from the inside to the outside and ensure that it will have that consistency moving from orange to blue? So the mechanics to that is very interesting. So away we go.
Well, that sounds like a good toy. Brilliant. Right. Well, we're going to get straight into our questions. We've got lots of questions for both of you this week, and we're going to start with one for Nira. And this is a very good question, and it's exactly the sort of question that we are here to answer. It's from Melanie, and Melanie says, "This might be a boring question, but I'm curious. What does a full-time mathematician do all day? I assume there aren't any physical experiments to do, so are you just trying to work stuff out?"
Oh my word!
What are you all doing with your days?
Okay, that all depends on the type of mathematician that you are. Now, with myself, I'm a what's called a math. I've been a professional mathematical modeler for over 25 years. And so what I do is I look at real world problems and I'll convert those real world problems into mathematics, solve it using mathematics, and then apply the solution into the real world. And sometimes some people will come up with something crazy like, Nira, there's going to be an airplane somewhere around the world falling out the sky. Can you come up with a mathematics to stop this problem? Or there's a pipeline about to explode. Can you come up with a mathematical strategy to solve it? Or it can be something very very mundane, where I just need to write, let's say, a mathematical algorithm. So it's constantly solving different mathematical problems at different stages. But yes, some can be quite extreme, some can be quite mundane, but all of it is exciting. But yes, very much I'm a mathematical modeler. So it tends about seeing a problem, formulating the mathematical solution, trying to write, let's say, a simulation mathematical algorithm. Sometimes, let's say, doing presentations, explaining to the experts or non-experts, saying this is how you actually apply the solution, and writing up reports. But it's very much day in, day out mathematics.
So there's this interesting idea here, though, isn't there? Which is sometimes quite hard for people to grasp, which is that we see the physical world and it's got dogs and clarinets and trees and so on in it, and mathematics is all these symbols. But there is this translation where we can use, the laws of physics or the rules that we observe, and we can say, well, we can represent, what this tree is doing by a rule, and we can basically write that rule in mathematics, and then we get to play with it in the world of maths. That is more or less that kind of process, right?
Yes, I mean, sometimes you don't even have to go. Let's say the laws of physics. Sometimes it's let's say a logical argument, because what somebody came up with a nice quote saying, and deep enough into anything, you will find mathematics, and that's my role, is to go down deep enough to find the mathematics. So it's just not necessarily has to be, let's say, the law of physics. It may be a case of coming up with a logical argument. Here's a logical argument, convert that into, let's say, an algorithm, run the simulation. Sometimes trying to find, let's say, the optimization of some objective, then applying that solution to the real world and to see how the two actually relate together. If it doesn't relate too well, see, where did I make my mistake? Did I make a mistake in my assumptions? Did I make a mistake in my logical argument? And that's the role of a professional mathematical modeler.
And just how did you get into that? Just while we're on that topic, how did you get started on all of that?
Well, I mean, I was doing my mathematics degree, and one of the modules was mathematical modeling, and I thought, wait a minute, here's mathematics, which done is very much experimental, and the problems are not closed. It's not, this is the answer and it's right or wrong, and you have to come up with it's almost like, because at one time I wanted to be like a lawyer. It's almost like being a lawyer. You're putting together an argument and you're using mathematics to do it, and I found that really exciting. So then I went and did an MSc specializing in industrial mind. Then I decided to go out in industry and solve real world mathematical modeling, and I went all around Europe doing so. And that's how I got into it.
Brilliant. Well, we'll have more maths in a second. We've got a question now for Helen. Another very good question, and it's a question from John's son. How could you do an operation on a fish? Would you need to be underwater?
That's a great question, and the fact that this does actually happen, I think that's what people do. I mean, I think that's great if you have pet fish. And you love them and look after them as much as you would any other pet. But yes, so there are vets who will deal with problems with aquatic animals. But you don't have to do them underwater. What you basically can do is that you can pull them out of the water as long as they stay moist. Damp on the outside, so you can kind of spray them with water, and then you just need to put a sort of tiny hose pipe into their mouths and let the water flow over their gills, and they can keep breathing. Now, the really cool thing, though, I think, with all of this is to put a fish to sleep, to give it an anesthetic, which they do as well. That's something else I've written about in one of my books. Is there's this myth that fish can't feel pain. And that has been around for a long time, and science has taken quite a long time to catch up and really show that fish do have pain receptors. They're able to perceive stressful situations, painful situations, and they can suffer as a consequence. So, of course, you can't just go cutting up a fish that's still awake. But to put a fish asleep, you don't have to inject it with anaesthetic. You can just put it into a bath of anaesthetic-laced water, and it will absorb it through its gills. So that's what you do. You can you pop some anaesthetic into its tank, and they will fall asleep. You can pop it out of the water. As long as there's water still flowing over its gills, it'll stay alive, and that's fine. And then when the operation's finished, so people do things like remove tumours from goldfish, things like that. And then to wake it up, you just put fresh oxygenated water over its gills, and it should wake up.
So it's basically like a gas mask. In the days where you used to have those, gas masks, they're breathing the anaesthetic rather than having it injected into them.
Yeah.
And what about, I mean, while we're dealing with that, putting a fish obviously raises the question of whether fish sleep. So is the I don't know how in-depth your knowledge about fish anaesthesia is, but do fish sleep? Is there an analogy of putting a fish to sleep, or does it just work differently for fish?
I don't know an enormous amount about what's going on when fish sleep, but we know that they do. They certainly are. I mean, you get nocturnal fish and you get diurnal fish. And so, for example, on like a coral reef, you'll get this switch over between the daytime active species and the night active species. And, at the time when they're not active, they will hide in the reef, and they do look like they've gone to sleep. You get things like parrotfish, which actually blow themselves a sleeping bag out of mucus, which they hide inside when they're sleeping, because they're pretty unresponsive at that time too. I mean, that's basically what we know about the state of sleep, is an animal that, if you give it a poke and it just doesn't move, so it's knocked out. And these parrotfish, that's the case. And we think they make these slimy balls to protect themselves from parasites. It's probably quite smelly, and it stops the smell of the fish from being obvious in the water. So things like snails will actually come along and try and suck their blood, which is lovely. But this protects them.
It's such a lovely question. We'll move on. I mean, yes, the whole question of fish sleeping is interesting. We'll move on to a slightly related fish. This is maybe what happens when the operation goes wrong, and it's from Ben. And Ben wants to know, where are all the dead fish? Because he thought most fish float when they die. At least that's when people's goldfish dies. That's how you know it's dead, right? So shouldn't the ocean and beaches be covered with old dead fish?
Oh, that's such a great question. I mean, it is a bit sad that we know this, because if you're goldfish, something's not right. Although actually, it might not actually just be dead. It could be that they've got a problem with their swim bladder. So a lot of fish have these basically gas balloons inside them, which help them to float rather than sink underwater. So it means they can save energy. So most fish, most of the time, want to be kind of neutrally buoyant. So that way they can save energy and not have to be constantly swimming.
So that means they're neither floating nor sinking. They're just kind of sitting in the middle, wherever they're put.
Just hover there. Yeah, exactly. So, and that's what you want to be when you're scuba diving as well. And that's when you really get that sense of flying underwater, if you can make your buoyancy neutral, so you don't sink or float and you're just hovering there. And it's a lovely sensation, as I'm sure you know, Helen, how wonderful it is just to feel like you're flying around underwater. So if you've got that neutral buoyancy, and fish do this with their gas bladders. Divers have to have a jacket on the outside which we fill with air. So I mean, one diseases that fish can have is of the swim bladder, so that if it gets too full, then they pop up to the surface. That said, dead fish do initially they do float, and that's because they are beginning to decompose inside, and so the bacteria that are decomposing their tissues are beginning to release gases, and that gets trapped inside them. It's like they are still a little balloon. Their whole body lets that gas stays inside, and they float. They don't stay floating. I think that's Ben's question, is because eventually that gas will get out one way or another.
We're not going into specifics here about exactly how it happens.
Somehow that gas will escape. It probably will start to get eaten by something, or there'll be some way for it to escape, and then those fish will sink. And so they will end up on the bottom of the sea. And that's actually really important. And we now know all sorts of sea creatures, whether it's fish or whales, turtles, when their remains land on the bottom of the sea, especially in the deep sea, it brings really important food. And we actually know that there are amazing, unique ecosystems that have evolved specifically to feed just on the dead bodies of things like big things like whales are particularly good because there's lots of food in a dead whale, but fish as well. And there are these armies of different species that come in, waves of different species that will be the first scavengers. Then later on, you get other things that eat the bones. There are worms that have specifically evolved to eat the bones of whales and other species. And there's like dozens of species, which we're finding more all the time. I was in the Gulf of Mexico a couple of years ago on an expedition and looking into the deep sea, and we put down alligators, dead alligators, for the first time into the deep sea to see what would happen to them. And about 6 months later, we went back and looked, and we found 2 new species of these bone-eating worms that no one had seen before.
They're suddenly having a day. We've never seen one of these before. Let's get stuck into that.
So yes, it's really important for those dead things to end up in the deep sea, and there are these ecosystems that really rely on that source of food. So that's really what happens to all those dead fish in the end.
Well, I think there's also another part of Ben's question, which is that you've got to ask why they died. And I think that most fish in the ocean probably don't die of old age. You know, they die because they get eaten, or a lot of them. So there's also, if something ate it, then I think, you know, all the gas, as you pointed out, isn't going to build up. It's just going to sink straight away. So then your fish goes straight down. So generally living matter is more dense than the ocean. That's really, I mean, it's one of these fascinating ideas about the ocean, isn't it? That everything's basically raining down. All the useful bits, all the nutrients are constantly raining down towards the surface, away from the sunlight. Anyway, right, we can't spend too long on ocean stuff, even though you and I could clearly talk about it for a long time. So we're going to come back to Nira. And we've got a question, Nira, from David Turner, who says he once saw a talk where someone compared calculus to Darwin, in the sense that once you understood Darwin, you can make sense of all of nature. But they never really explained how that related to calculus. He says he had to do it at school, but he can't remember the rest of it. Never mind how the idea it's the key to the rest of math. So what's the deal with calculus? Perhaps maybe just in broad terms, tell us what calculus is to start with.
Okay, calculus. I mean, calculus is to do is, you know, if you want to find the area of a function, or you want to find the gradient of the function, or even you want to go into more, let's say, more n-dimensional areas and volumes, etc. That's very much what calculus is. And also when you're talking about maximization, optimization, minimization, that is very much is calculus. Now, the teacher that actually said that, I would need to speak to that teacher and saying, really, I want you to explain that a bit more. However, there is one point that he's probably quite right. He's like, I remember, you know, breaking down one time, and this road assistance company actually picked me up, and we were on the motorway, and we're stuck in traffic, and the gentleman says to me, he goes, I don't understand why I'm stuck in traffic, and then the traffic starts moving, and we can't see why why this has been stuck in traffic, and he doesn't realise that actually has to do with his calculus. And I have to explain to him about running water into a bath, and you say you got a tap, and you're running the water into a bath, and you plug the bath, and the water rises, and then you unplug the water, and then the bath water goes down. See, the part that you are in the bath, let's say you're a particle of water, you don't see where that, you know, by the time you reach the plug, you don't realize that the reason why I'm going down that plug, you know, it's because the plug hole was actually plugged. You know, you just see an empty space. And I'm saying it's the same principle when it comes to, you know, a traffic jam on a motorway or any road system, and that all has to do with calculus. You know, it gives us an understanding how things change with time, or change to a respect to some other variable. So I hear what he's saying. I don't absolutely agree with the teacher. We need to speak to that teacher saying, listen, there are so much other aspects of mathematics that you are actually excluding that doesn't relate to calculus. Mathematics is much more wider than that. But I can kind of get where he's going, but I don't totally agree.
Well, I think as a physicist, we use calculus, as you said, about things that are changing. So if nothing was happening in the world and everything had just settled down to equilibrium, we wouldn't need calculus because it's all staying the same. And the times we use calculus, like you said, are when the bath analogy is really good, when things are changing and we need to sort of work out how all the different changes, what the effect of all of them is together. And so, yeah, but yes, there is quite a lot of other mathematics in there. But it's one of those mysterious bits of maths, isn't it? Like people remember calculus partly because it's this kind of alien word as this weird thing that is the difficult bit. How much do you come across that? Like the idea in maths that there are some difficult bits and people never really get across. They see them as hurdles that they never really got across, and they think there must be something exciting on the other side, but they never got there.
I mean, so for instance, you know, people's journey through mathematics, you know, you start off with numbers, thinking you did the long multiplications, you go up to the 12 multiplications, and then all of a sudden that horrible teacher introduces algebra and thinking, oh dear, you know, why are you introducing algebra? And then all of a sudden they introduce calculus, and then it goes on to the, but seeing as end of the day, all of mathematics is beautiful. You know, all of mathematics is beautiful. And it's not, and yes, you get these concepts which are challenging, but it's like a language. Mathematics is a language of science. The person that came up with calculus came up with a way to say this is how we can actually express it in this form. And, you know, I believe it was Leibniz. Well, Newton and Leibniz did it at the same time, but they argue who came up with the with the differentiation first. So yeah, that's my views on the matter.
Well, the nice thing about that invention, isn't it, is that there's actually a shadow of that still in mathematics today because of the symbols. Because one of the things that confuses, you know, I still find myself explaining to students in the first year at university is that there's different ways to write the same thing. And one of those came from this character Leibniz and one lot came from Newton, and we still use both of them interchangeably, and so it's kind of written into the mathematics.
Yeah, but it tends to be the one Leibniz tends to be the one that's which is more popular. You know, the dy by dx. You know, if we're thinking what do we prefer, x dot or dy by dx, and most people are going to say dy by dx. You know, so that's, you know, it has a much more artistic, much more elegant. It's much more, you can actually see it flowing more. Now, the thing is with the Newton's, you know, x dot, you know, once you move into the area of partial differential equations, what you're going to do, x and a half of a dot, you know what I mean? So
well, we can now have a debate on Twitter among those of you who do remember about which format you remember. I think both have their advantages. Depends what you're doing. Okay, let's go back to some ocean things. Another question for Helen from someone who has a quite, I mean, it's an acronym rather than name, JSYD 2015. So, and Helen, the question is the salt water content of the ocean the same all over the globe?
Ooh, good question. So the oceans are very salty. On average, everywhere, it's something like 35 grams of salt.
On average, yeah.
But that is the average, and it does vary. So it's not a silly question at all. There are all sorts of factors which influence the salinity of the ocean. And Helen, I know you know a lot about the.
Yeah, I asked you the question and I felt bad because I'm the physical oceanographer.
It's your territory, so maybe I should hand it back to you. But I know that, you know, that the difference in salinity is very important. I'll quickly mention why some of the salinity varies, and perhaps I'll hand it back to you to say how important that is. But I mean, simple things like when it rains a lot. So there's a strip of the equator where it rains a lot, and the oceans are slightly less salty. And we know this. There's a satellite actually that measures salinity from space. So we've got these global maps now of the sort of surface salinity of the oceans. And there's a kind of a slightly more dilute part in the equator. I think in the poles there's lower density, lower salinity because of the melting of ice sheets and glaciers, that kind of thing. And then by where there's rivers coming out, so at the Amazon, for example, where all that water's coming out of the Amazon River, the salinity of the ocean is slightly less. And then we've got really big, strange, which for a long time people couldn't really explain, things like that the Atlantic is slightly salted than the Pacific. And one possibility for that is that it could be the Andes mountain range, which is so weird to think that what's going on land affects what's happening in the ocean. But the theory is, and I think they've done studies of this, is that the rainwater that's coming in off the Pacific hits, essentially, it's coming eastwards and hits the Andes and then falls back down as rainfall. So it sort of keeps diluting the Pacific, whereas you haven't got that going on in the Atlantic. And so the salt levels there don't get diluted by that sort of that huge rainfall that you get in the Pacific. But salinity is really important, isn't it, Helen, for how the oceans work, really?
Yeah, and so there's a point here which is one of these incredible things that I think everyone sort of forgets, which is the salt composition of the ocean is pretty much identical everywhere, which is astonishing all by itself. So we know salt is sodium chloride, but actually if you look in the ocean, it's mostly sodium chloride. But then there's potassium and, bromine and bits of iodide and all these other, like this mix, but the mix is exactly the same wherever you go. And what that tells you is that the ocean is basically really well mixed for salt. The salt is there all the time. Like you said, it's the fresh water that comes in and out that changes how salty different places are. And you get places like the Mediterranean, which is very salty because there's lots of evaporation, and then that kind of pours into the Atlantic. And then the Baltic Sea, which is kind of hidden up underneath Sweden, is fresh because it's got loads of river inflow, and so it's got this ridiculously low salinity. So it doesn't vary very much, but like you say, it's really interesting. But just to come back to a fish question off the back of that, because I think this is really interesting, and this is something that you will know more about than me. And it is the fish that can go from saltwater to freshwater. So salmon, for example, there's this there's a word that isn't androgynous, but it's what is it? It's an awful word. I can't remember.
It goes both ways, doesn't it?
Andromagynous or something.
Androgynous.
Yeah.
It'll come back to me. But yes, there's a word for when they
go both ways.
To freshwater, and some that go from freshwater to salt, so they can go both ways. Yes. Did you want to know the word? Was that the question?
Yeah, well, it's just really cool, isn't it? Because in one environment, they're desperately trying to get rid of the salt, and on the other one, they're trying to keep hold of the salt. And they, marine creatures are really, there's a lot of adaptation just to deal with it being such a salty environment.
Yes, androdromus.
Someone on Twitter has looked this up already and is about to tell us the answer.
Awesome, thank you very much. Yes, so no, it's really fascinating. So for species that live in the ocean, the real problem is too much salt on the outside, and their body concentration is less than that. So you're basically going to be losing water by osmosis to sort of try and, it's that biological process of water diffusing out of a body across the biological membrane to sort of try and balance out these differences in salinity. And so fish have these mechanisms to try and avoid that water loss, and they will, for example, just drink lots of water and then have a mechanism for expelling the salt. So we don't have that as human beings. We can't do that. Our kidneys are not we have not adapted to consuming vast quantities of salt water. It's very bad for us. We need to drink more fresh water to actually get rid of the excess salt. But marine fish have adapted to this very well. So you take a salmon and then you move it into fresh water because that's where it goes to spawn, and everything is reversed. And so basically they have to suddenly switch their biology. And by doing so they have to sort of stop drinking, and they start peeing. This is the physiological adaptation for moving into fresh water, is because then instead of losing water, they're basically taking on and on lots of water because their bodies are now more concentrated than the water around them. So there are physiological changes that take place, and it does take them a little while. So they often have to hang around in estuaries and sort of adapt their biology before they can move into fresh water. And interestingly, I don't know if we've got time to talk about the deep sea. There is a kind of application.
Very quickly, because we have to get back to some maths, but go on.
The same thing happens as you go deeper underwater, because one of the ways that fish deal with pressure is by putting lots of these chemicals in their body called TMAO, trimethyl oxide, and that increases the concentration of their tissues as well as protects them from pressure. But there comes a point where they can't have any more of it because it makes them too concentrated, and it would be the equivalent of a freshwater fish moving into the ocean. We think there's like a maximum depth that fish can get to, and that's as deep as they've gotten. It's about 8,200 meters. It's the deepest we've ever found a fish, which is the theoretical limit based on this biology of what they put in their tissues to stop themselves from essentially collapsing under the pressure of all that water. It's pretty cool.
So if you'd ever wondered whether you could find a fish right in the ocean, apparently there's your physiology of why it doesn't happen, because the deepest part of the ocean is a bit deeper than that. Okay, let's come back to some mathematics. Nira, there is a question from Ashley, which is there a particular thing in mathematics that you know to be correct, but it's so unintuitive that you sort of don't believe it? He's thinking of the Monty Hall problem. And he says, or he or she, they know the maths behind that, but it still seems like it's the wrong answer. I have to say, I don't know what the Monty Hall problem is, although I feel like I should.
Okay. First things first. Let me explain about the Monty Hall problem. Right, the Monty Hall problem. It was based on a quiz show that was done in America. I can't remember. It was in the 50s or the 60s. And what happened was, the contestant will go in front of 3 doors, and then the show host would say, right behind one of these 3 doors is a, let's say, a goat, and the other one is a nice car. And then what the contestant does, he chooses one of the doors, and then what the host will do, he will open up one of the doors which definitely has not, that definitely has not got a goat or a car, and it says to the contestant, would you like to choose a different door? Would you like to change? And if the contestant says yes, then they'll change to another door, and then what will happen? What we found out is that they actually increase the probability of them winning the car if you actually switch, as opposed to remaining where they are. And this has confused so many mathematicians and statisticians over the year, because they would argue that surely it should be even, but it's not the case. So that's the Monty Hall problem. Now the thing is, even though, let's say, intuitively, you're thinking that the probabilities are the same, if you do, let's say, run a simulation, and you look at the two strategies, you actually see, yes, you can, it's better to actually to swap. And then another problem is called the birthday problem. Let's say, for instance, you have a number of people in the room, and they all got an even chance of being born on the same same day, the same day. And you say, well, how many people should you have in the room? So there's a 50-50 chance that 2 people will share the same birthday. And people intuitively thinking, half of 365, that's it, no problems. Well, the answer is actually 23, and people thinking, how can it be that low? Yeah. And again,
so let's be clear here. So if you have 23 people in a room, in that situation, the chances are that 2 of them share a birthday.
Yeah, there's a 50-50 chance that 2 of them will share. Yeah. So the key is, intuitively you're thinking, well, that can't be the case. Again, if you do, let's say, a simulation or go into the proof of the math, you can actually see, yeah, it is true. It is 23. So that probability is one of those probability freezes, one of those things that throws up these crazy things, which is what makes mathematics very exciting. I mean, another thing, if you just want to go on another field of mathematics, is Ramanujan's pi theorem, and you look at it and you're thinking, how on earth does this formula, made up of all of these integers numbers, and it's an infinite series, can approximate pi 1 over pi? And so that's the beauty.
So we should say that what this is that pi is obviously that it's 3.14, and then it goes on forever with lots of different numbers. And this formula you're talking about is a very well-behaved formula, but it allows you to work out what pi is. And it's just that there's a disconnect between the weird chaos of pi and then this very specific formula that tells you what it is.
Yeah, because he's got this formula made up of factorials and integer numbers, and there's an infinite series, and it's all combined together, and somehow this formula is a good approximation of 1 over pi. So you could use it to work out pi, and you're thinking, how did he get from that part to 1 over pi? Again, it's, when you look at it from an intuition point of view, it's not easy. But when you actually do the numerical simulation, you can actually say, oh yes, it's actually true. Or if you're going to go and have a look at the proof, you can actually see it's true. But when you actually first see it for the first time, you're thinking that can't be right. But any good scientist, any good mathematician would actually go and take that step and actually investigate. And that's what's the beauty of mathematics is.
I have to say, I really annoyed Matt Parker once. I think it might have been the first time I met him years ago. Winchester Skeptics in the pub. He came to give a talk, and he presented the thing with the birthdays that you just said. And I think there were probably about 200 people in the room, and he had just gone through the maths to establish that if there were 23, it was odds on someone, should share a birthday. And I stuck my hand up and said, I've never met anyone that has the same birthday as me. Can we see if there's someone in this room? And he was like, yeah, okay, whatever, go on then. And nobody did. I've always wondered what it is. I did find out I shared a birthday with someone at their funeral, but I don't think that counts. And I think that since then, one person on Twitter who I have met in real life has told me they share a birthday, but I have never knowingly met anyone in person knowing I share their birthday, and it really annoys mathematicians because the statistics say that's not supposed to happen.
Well, I mean, then the thing is, one of the things we have to understand is that we have to step back and recognize the assumptions that is made in that argument. The assumptions in that argument is assuming that the people's birthdays evenly distributed around the year. Now, if we actually did a statistical analysis of it, the birthdays are not evenly distributed, so henceforth the birthday that you're born on is not evenly distributed. That's why you'll find it hard for somebody to share the same birthday as you. But if you take the case saying if the birthdays are evenly distributed, away we go.
Brilliant. Okay, let's go from birthdays back to a slightly more serious question from OAUS. I don't know who or what that is. But Helen, they say there's increasing talk about deep sea mining for minerals that might be used to make solar panels for renewable energy. Isn't this just robbing Peter to pay Paul?
Such an important issue at the moment, and I've actually been thinking about this a lot lately, and I've written at length about it in my next book that's coming up. So there'll be more about it there next year. But really, this is a new pressing issue, an environmental issue that's kind of coming up really quite quickly. So for those of you who haven't heard of it, basically there are mineral deposits in the deep sea in various different habitats, including extraordinary, unique places, the hydrothermal vents, which are these cracks in the seabed where boiling hot water comes gushing out. And there is life that is persisting on these chemicals in these extreme conditions. We've only known about them for about 40 years, and we're still learning so much. So hydrothermal vents are one place where there are metals in these big rocky chimneys that form at the cracks down in the deep sea. Also, abyssal plains are covered in things called manganese rocks. I remember when I was at school years ago, we talked about these manganese nodules that were sort of scattered across the abyss. And back then, the idea I had was that was all there was. There was just rocks and mud and nothing else. But we now know that these are also the basis of really important ecosystems. Things like deep sea octopuses use these rocks to essentially fix their eggs too. So it's like an octopus's nursery, and the rocks themselves have species living inside them. It's a really rich but very little known ecosystem. And also seamounts, these sunken underwater mountains, these extraordinary geological features in the deep sea are also potentially targets for deep sea mining. I guess, to sort of long story short, there's a lot to talk about with this, but what's being said at the moment by corporations that want to do this, that are thinking about trying to mine for the first time, it's been on the agenda for decades, but only now do we have the technology and possibly a reason, they say, to do this, which is this idea that we need these metals to have a green economy. So the argument goes that the only sustainable way for us to get rid of fossil fuels from our economies is to find these metals in the deep sea, which we will need, they say, for solar panels, electric car batteries, this kind of thing. The problem is that I have lots of problems with all of these assumptions. Firstly, that this is going to be more sustainable. We simply do not know this is the case. And all of the science unequivocally is saying right now that the chances are that it will have an enormous impact on not only on ecosystems, but potentially on the functioning of the whole ocean and the climate. The deep sea is incredibly important for the carbon that's locked up down there. We're really messing with stuff that we don't fully understand. So to say, oh, well, this is going to have less impact than mining on land, we do not have the science to back that up. Equally, the other part of the question is, do we actually need those particular metals? Things like rare earth metals, cobalt, which we find down there. And fine, we do need those at the moment for the way that we're currently making batteries, we're currently making some types of solar panels. But that doesn't mean that's what we're going to be using in the future. And I think a really important part of all of this debate about how we should be using the deep sea is the idea that we can innovate. And there are other ways of making solar panels, of having car batteries, for example, and so on. And we need to embrace those new technologies and say, well, let's find solutions that don't require potentially messing with this whole enormous part of our planet, with consequences that we simply don't fully understand at the moment. We've got really exciting potential new things like spray-on solar panels that don't require any of these expensive rare metals, which we could spray on walls and on car roofs and things, made from completely different minerals that don't require deep sea mining. So why don't we go and think about trying to find other ways of using our resources in a really smart way, rather than just opening up this whole new frontier?
Well, I think it's really important that it is basically as a red herring argument, because, as you say, the technology is such that we are not going to need those minerals. Like, things are changing. There's less and less cobalt in batteries all the time. Most of what makes solar panels anyway is silica, and there's certainly no shortage of that. It's a straw man argument, I think, that is just a distraction. That there's clearly no. Like you say, there are so many. We're making organic semiconductors. It's not necessary. So I'm going to go from that to a question which Jeremy posed. And if Robin was here, he would ask me this. But because it follows on, I'm going to ask this question, answer it, and one of you two might have an opinion. And Jeremy says that at some point he heard me ask me the question: how much better can batteries get with current technology? And is it the case for batteries that there's going to be the next big leap to stumble on something that we've not even thought of, which is sort of what Helen was hinting at, that we've always had this idea that batteries especially have to be made from these big heavy metals that are difficult and weird and have to come from somewhere else. And there is an enormous range of battery chemistry. The thing is, at the moment, it's all incremental gains. So, the next battery technology will get you 10% better or 20% better. There's no, as far as I know, and I've asked quite a lot of people about this, there's nothing that's visible at the moment in the minds of scientists which would make it 10 times better. So I think there's a combination of things here, that there are certainly ways to make cleaner batteries, to make them easier to recycle, to reuse all the things we've already put into batteries. Let's have those around again. But it's actually really hard with batteries to see the genuine game changers that will really, but it doesn't mean it's not out there. And there are enormous amounts of stuff we can do with the batteries we've got. So yeah, I don't think we do need to stumble on something we've not thought of. We can go a long way with what we know now, but we can't see that next step just at the moment. Okay, let's go back to the maths. And we have a question from Marcus Mercer, don't know what that is. Anyway, so the question for you, Nira, is how do we know that our mathematical understanding of the universe is true and not just applicable to the organic human brain?
Wow.
Deep philosophy for you here.
Deep philosophy. Oh, you need a philosopher on for this one. The key thing is how do we know it's true? All let's say all mathematical models, are based on assumptions and has limitations. And as mathematicians and as scientists, we always look to test our mathematics against what we actually observe to say, is it true? And then we conjecturize, saying, well, let's make a prediction. If our mathematics is correct, this is what we'll believe is to be true. And we're continually testing that. One of the things that you'll find is a mathematician will never become complacent, saying, this is my mathematics and there it is, and walks away, especially when it comes into mathematical modeling. So how do we know it's true? Seeing as the mathematics when we're talking about the solar system is always evolving, is always being challenged, and yet there are some things that we can say, yeah, this is true, and we got what we observed. This agrees with the mathematics. Away we go. So I don't want to sound like it's a bit of a cop out. I'm saying yes and no, but that's what it is. You
are saying yes and no. This is like get your blue and orange ball out again, and it's showing his answer.
There are some things where you can say it's been looked at, it's well understood, and until something very big or crazy comes along that she says actually your assumptions are wrong, or this is what you're dealing with is not a generalized case, it's a very specialized case. That's where it is. So that's mathematical. What he's talking about is not so much mathematics, it's more about mathematical modeling, and mathematical modeling is based on assumptions and uncertainty, and mathematical modeling is not about proof. Mathematical modeling is actually providing evidence, and there's all out there that actually shows that our conclusions is not absolutely built on solid ground. But at the end of the day, we're moving in the right direction.
Testing against reality. Reality's checking up on you, basically. You go, do that. So you need to rethink this.
Yeah. So that's what makes, like I was saying, I mean, over and over again, that's what makes mathematics exciting. Mathematics is not a cold, frozen subject. 1 + 1 = 2, and that's it. You don't know. Mathematics goes beyond. Mathematics go beyond that. It's an evolving and exciting subject. So yeah, that's my view on the matter.
That's your pitch. Mathematics.
Yeah. There you go.
Brilliant. More of that. Okay. So, Helen, next one. We're getting towards the end. We've still got lots of questions, so we're going to go a little bit quicker now. But Mark has a question. He says, every time I've been to an aquarium, I see these fish, although he's not sure that they're fish, that stick up from the bottom of the sand like little tubes, and they spit out tiny rocks, dust, and pebbles. What are they? What are they doing? Is that their mouth, or is it the other end? They're usually in tanks with things like clownfish. What's hiding under the surface?
I don't know what this is. I really don't. Little tubes. I mean, there are fish.
I think they might be. Are they bivalves? Is this a mollusk that's hiding underneath and punching, like filtering at one end and sending things out the other?
I really don't know. I mean, there are. It could be that, possibly. I can't think what this might be.
Worms. It might. There's those worms as well, aren't they, that sit down the bottom and filter, and then they sort of kick up little plumes.
Yeah, there are worms that sit in the bottom of all various sort of sandy beds. I mean, it's not. It certainly isn't. It can't be something like a garden eel, because they're quite big and they're quite difficult to keep in. I know you can get them in aquariums. These very long fish that sort of stick in burrows and stick their heads out. But they're planktivores. They eat the planktons. They don't spit out sand. There are little fish, things like gobies and jawfish, which will excavate little holes, and they will get mouthfuls of sand and kind of spit that out. But that's not a tube. So I really don't know. I'm very stuck. I'm a bit stuck on this one. Sorry.
Well, next time you go to an aquarium and you see one of these, try and catch a picture of it, and then we'll ask again.
Please do. Yes, that would be great.
But there's lots. One of the things about the ocean, and it actually goes back to what Helen was saying about the deep sea, is that all the interesting bits are hidden in the structure underneath the surface. And if you take a slice of the seafloor and kind of cut it, cut a slice through it, there's all these things and burrows, and there's all this 3D structure. But the problem is, firstly, it's all brown, and secondly, you can't really see it from the surface. And I find it really frustrating. Like, I've had this argument with producers on TV shows where you get this amazing sample of ocean sediment, and it's got these things and worms and stuff, and there's all these layers, but it's all brown, and they just look at it and go, oh, well, that's a bit boring. And you go, no, it's not. It's really interesting. There's all these things, and they're doing stuff, and they're recycling things, and the fact that they're brown doesn't make them boring. And it's this real problem with everyone looks at the colourful fish, but anything that's brown and in the sediment is sort of dismissed. Do you get frustrated by that, Helen, or is that just me?
I mean, I haven't come across the brown sort of colour thing before, but definitely the hidden stuff. I mean, that's generally across the board a problem with the oceans, and especially the deep ocean, is that it's out of sight. And I have to confess that, I mean, a lot of the stuff I write about is the kind of colourful fish, the exciting octopus, that sort of stuff. But equally, tapping into that smaller world as well, the microscopic world, is where the really fascinating stuff lies, and it is hard to bring that to life in a way. I mean, you've got to find ways of really making that relevant, and at least kind of understanding it and seeing it is a bit of a challenge as well. But yeah, it is hard. Yeah.
Okay, back to the maths then. So Dave L has a question, and which will please Matt Parker. He says, speaking as a layman whose knowledge of maths is basically from watching Matt Parker's YouTube videos, the Goldback Conjecture seems like it should be easy to prove. So why isn't it? And he clarifies, and this is very it's very kind of him. He's not asking you to prove it, just explain why it's difficult.
Okay.
So could you perhaps start with what the Goldback Conjecture is?
Let me see. Goldback. Now, is it saying that any integer that is greater than 2 can be expressed as a sum of 2 prime numbers? Yeah, that's it. Right. So how do we prove it? It's one of the hardest problems out there. So, okay, why is it so difficult? Well, the thing is, when you come in to a proof, most people, when they do a proof, there are 2 ways of doing preferred ways of doing proof by contradiction or proof by induction. Proof by contradiction, prove that it's not true. So hence we'll jump on the computer, run through all different cases, and then find an example where it doesn't happen. Now, I think they've gone up to something, they've gone up to something like 10 to the power 18, and they still can't, say it's true all the way up to the number 10 to 18, and the computer's probably given up by then. So we can't find a counter example. So that's one. We can't find a counter example. Proof by induction. Right. Start off with an easy case. Start off with a general number. So let's start off with a number n, which can be expressed by the sum of two prime numbers. And let's say one of those prime numbers is 2. And then look at that other number. Look at the number and say add 1 to it. Can we still express it as sum of two prime numbers? And yes, because all we need to do is, instead of using 2, we use 3. So in that case, in that specialized case, it's all easy. But then let's say, for instance, let's start with 2 odd prime numbers, yes? And then if we increase the number that we're trying to do sum by 1, but if we put 1 on the other side and add 1 to the odd number, that comes as an even number. Now, the even number, apart from being 2, cannot be a prime number. And so henceforth, you can't use proof by induction, because then you have to start looking at thinking, well, what other 2 prime numbers can we use in? And you're going all over the place. And then you get into this case of saying, well, how do you predict what's the next prime number? And nobody really knows about that. So you're getting into a whole different realms of mathematics. So it's like you come into another problem, which is goes to another problem, you're solving another problem, solving another problem. That's why it turns out to be very difficult, because the two traditional ways of doing it cannot solve it. You have to come up with a whole different style of proof to solve that problem, and that's why it is difficult to prove.
That is a very good answer. Thank you very much. One of my favorite so the proof by induction is one of those things that people hear at school, and there's a lovely limerick that has been knocking around for years. I don't know where it came from, but it goes like this. A friend who's in liquor production has a still of astounding construction. The alcohol boils through old magnet coils. He says that it's proof by induction. Which is a very technical joke, but it's a very, very good one.
Yes, very, very much so.
different type of proof by induction, but perhaps more appealing for some people. Okay, right. We have a question, Helen, and this has a very long answer, but you've only got a couple of minutes. From Patrick Chalmers. What political structures and changes to our systems of government would give our species a chance of reversing oceanic heating, marine biodiversity collapse, and pollution by plastics, agriculture, and industrial waste? So basically, please, can you solve the problems of the world in less than 1 words?
No problem. Yes. You want the political structures
of governments? What? Yeah. Is the approach wrong? I think what he's asking about, perhaps, or hinting at, is perhaps holistic views of looking at the world rather than. I don't know. But yeah, political structures and changes to our systems of government.
To fix the whole lot. Well, I mean, we can't do much worse than we are at the moment in many ways, I have to say. Perhaps that's a little bit too strong. But yeah, I don't know. I think it's going to be a holistic view we need to take. We've got to change so much about how we value how the resources of the earth are valued. Perhaps if we just sort of focus in on the using part of things, to bring in the costs would be one thing to do, which we just don't do at the moment, that you can take from the natural world and make money from that, but any kind of impacts that come as a consequence, whether that's carbon released or plastic or anything else, doesn't come on that score sheet. So it can still seem to be a profitable thing to do. So maybe that's one aspect that really needs to be changed, is to really bring those costs into those decisions that are made about how we use this wonderful planet of ours and all its resources. But it's such a difficult thing. Perhaps another whole book I will debate.
Yeah. Well, yeah, I think a more holistic view is seeing ourselves as part of nature and not separate to it. A lot of it's that sort of thing. And also the other principle I think is very important is forgetting that we can't have the attitude that away is somewhere else. Like I did a whole thing about poo I think it was last Christmas at 9 Lessons, where if you look at Bazalgette sewers in London, they were brilliant because they took the poo away, and this was a brilliant solution for the City of London. For 150 years, all the poo has gone somewhere else. And the problem obviously with Bazalgette's system is that when it rained more than expected, or there was more poo than expected, the system overflowed into the river, and that was just carried out to sea. And no one ever thought about away being a part of our own world because it was away. And I think the idea that there's somewhere else is one that we've got to get rid of. It's basically, you don't poo in your own backyard, right? Backyard. So don't put poo in the ocean because it is your backyard. You know, it's that kind of thing. Okay, very quickly, Nira, one more for you. In high school, we were taught to use sine, cosine, and tan as though they were all equally useful. As an adult just generally interested in science shows, I often heard sine referred to, and occasionally cosine, cos, but never tan. Where are they used?
Well, they're used place everywhere. Used in architecture, used in radio waves, used on your TV, used on the CD. You just have to just end it with just saying that mathematics is indisputably the greatest subject in the whole wide world. So just get used to it, and that's it.
That is. I'm not sure we're going to let you get away with a blank. This whole point of a science question and answer session is to have questions and answers.
But there's your answer. There's your
We're
answer.
going to question you on your blank.
That's your answer. That's your answer. That is your answer. Why do you need sine, cos, and tan? Because mathematics is indisputably the greatest subject in the whole wide world. There you go.
If you ever write a maths textbook, maybe you already have, I don't know, it's going to be the shortest textbook ever, isn't it? Because maths is awesome, the end. That's going to be it.
Bestseller.
Okay, right. Well, that seems as good a place to end our investigations of the natural world for today. So, very quickly, Helen, what's your new book going to be called?
It's called The Brilliant Abyss, and it's a celebration of the deep sea and the problems as well that we're causing down there.
And when is that going to be out?
Comes out in February 2021 here in the UK, and then a bit later in the US and everywhere else. So.
And Nira, have you got any projects on the go that you'd like to tell everyone about?
Yes. At the end of next month, we're having a virtual conference called the Black Heroes of Mathematics, being put on by the IMA, the London Mathematics Society, the British Society for the History of Mathematics, and the International Centre for Mathematical Sciences, where we have black mathematicians from all around the world doing a virtual talk about mathematics. Both technical and testimonial. So that'll be a very good conference that we're putting on.
Brilliant. And can you maybe if you put the link on Twitter or tell us the link and we can help share that, that'd be brilliant. Okay, so quick reminder again, there's Patreon if you'd like to support us. There's a tip jar. All the links are below the bit of the screen you can see us on. Don't forget to look for Paul Nurse on the first science book Shambles, the genetic Shambles on COVID. Next week we will be talking about particle physics with Dr. Linda Cremanosi and Achintya Rao from CERN. So get your particle physics questions out. And again, there will be this very big announcement on October the 5th from Cosmic Shambles. So keep an eye out for that, although you will find out a little bit earlier if you're a Patreon subscriber. And that is it for this week. Thank you to everyone who sent in a question. Thank you to our two fabulous guests, and we'll see you next week.